This video is about the singular value decomposition. The singular value decomposition is a matrix factorization. It's a way to write any matrix as a product of other matrices. And it's a factorization that has a lot of applications. And in this video, we're just going to say what the singular value decomposition is and explain how to find it. But first I have to say what singular values are. So let's say that A is any m by n matrix. A doesn't have to be a square matrix, it's just any matrix. Then we know that we can get a symmetric matrix from it by taking A transpose A. Right? This is a symmetric n by n matrix. I think this is a little too... Is that really the next boldest? Okay, well, one fact we need about A transpose A, we need something about its eigenvalues. And the statement is that every eigenvalue lambda of A transpose A is non-negative. So it could be 0 or it could be positive, but it's never going to be negative. Okay. Let's prove this statement. So lambda is an eigenvalue, so therefore there's some unit eigenvector, right? You just take any eigenvector with eigenvalue lambda and divide by its length. So let x be a unit length lambda eigenvector of A transpose A. Now notice that A itself is not necessarily square, right? So A might not have any eigenvalues or eigenvectors. But A transpose A does. And we're letting x be a unit length eigenvector of A transpose A with eigenvalue lambda. So what that means is that A transpose A times x is equal to lambda x. Now the trick is to multiply both sides on the left by x transpose. Okay, and you can check that the dimensions are going to work. So A transpose A, by the way, it's an n by n matrix, right? So x is some vector in Rn. So x transpose is the 1 by n matrix. So this is an allowable operation. X transpose A transpose AX equals x transpose lambda x. Now I can pull out the lambda from the x transpose lambda x and get lambda times x transpose x. Well, x transpose x is just the length of x squared, right? It's the squared length of x. It's the dot product of x with itself. And so this is going to be lambda because x has unit length. Unit length implies that x transpose x is equal to 1. So it's lambda times 1, which is lambda. On the other hand, we can also express x transpose AX as AX in parentheses transpose times AX. And this is just the dot product of AX with itself. So it's the length of AX squared, which of course is greater than or equal to 0. And so therefore, we've shown that this expression, x transpose A transpose AX, is lambda and is greater than or equal to 0. Therefore, lambda is greater than or equal to 0. In fact, so that's the proof. So in fact, lambda is we actually showed that whenever you have a unit length eigenvector and you take the ax, now ax itself might not have unit length. But if you take a times x and then take its length squared, it's equal to the corresponding eigenvalue. And, well, maybe I shouldn't say in fact. You know, we actually have shown that this is true because they're both equal to x transpose a transpose ax. So what we're going to do is we're going to take the square root. So if you take the square root of lambda, that's just going to be the length of a times x. Okay. So that leads us to the following definition. So let's look at a transpose a and choose an orthonormal basis. Okay, so we're done with the proof, right? We proved that above here, and now we're moving on. This symbol means that it's the end of the proof. This box. We're ready to move on to singular values. Okay, so we choose an orthonormal basis for Rn consisting of eigenvectors of A transpose A. Remember, we can do this by the spectral theorem, right? It's the A transpose A is a symmetric matrix. It's a symmetric real matrix, so it has to form Q lambda Q inverse, and those vectors, the column vectors of Q, those form an orthonormal basis for Rn consisting of eigenvectors of A transpose A. Okay, so let's call this basis V1 through Vn. So remember, this is just, if you take Q in the A transpose A decomposition, you're taking V1 through Vn to just be the columns of Q. That's what we're doing. Okay, and then we call the eigenvalues lambda I, as usual. So let lambda 1 through lambda n be the eigenvalues. But what we're going to do is we're going to reorder these eigenvalues so that the lambda i's go in decreasing order. So reorder the eigenvalues if necessary if needed so that lambda 1 is greater than or equal to lambda 2, which is greater than or equal to lambda n. And of course, these are all, we showed that these are all non-negative, so they're all greater than or equal to 0. Okay, remember we're looking at A transpose A here. Okay, so this is Q, just to emphasize, this is A transpose A is Q lambda Q inverse. Okay, so now we define for each I, sigma I to be the square root of lambda I. And these sigma i's, these are called the singular values of A. And we've shown that this sigma I is the length. You can think of this as the length of A times VI. All right, so the singular values of A are what you get by taking A transpose A, finding the eigenvalues, and then once you know that these are non-negative, you can take the square root, and those are the singular values of A. And using that, we can define this matrix, which is sigma. It's called sigma. And what it is you take the singular values of A. And okay, first I'm going to write this down and then I'm going to explain it. So you take this diagonal matrix where you take the singular values from sigma 1 to sigma r. So r is the rank of A. Okay. So you get this r by r matrix like this, and then you fill in the rest with zeros. So you have zeros everywhere. And we're defining this so that this is an n by n matrix. So here you have r rows, and then here you fill in these m minus r rows with 0. And then you have r columns, and you have these n minus r columns that you fill in with 0, and that gives you m by n matrix. So why does it go to sigma 1 to sigma r? So the point is that when you're listing these eigenvalues, these n eigenvalues, you're listing them with multiplicity. So some of the eigenvalues might be repeated. So for instance, if you had the n by n identity matrix, it would just be 1. Your lambda 1 to lambda n would just all be 1. Your lambda 1 is 1, lambda 2 is 1, lambda 3 is 1, etc. If your matrix is not invertible, so if it's singular, then 0 is one of the eigenvalues of A transpose A. So I'm sweeping some facts under the rug. So one of the facts I'm sweeping under the rug is that the nullity of A, so the dimension of the zero eigenspace, is equal to the nullity of A transpose A. And that's, and the number of eigenvalues, when you count with multiplicity, that's 0, is going to be n minus r. So basically, if A is, let's see, if A transpose A is not invertible, then you're going to have some of these lambda i's will be 0. And it turns out that you're going to have n minus r zeros. So only the first r singular values are actually non-zero. So what these are the non-zero singular values. Let's write that down. So sigma 1 through sigma r are the non-zero singular values. And sigma r plus 1 all the way to sigma n are all 0. That's what's going on. Okay, I didn't prove that, but let's just take it for granted. So that's the matrix sigma. It's an n by n matrix. And now we're ready to state the theorem, which is the singular value decomposition theorem, which is there exist an m by n orthogonal matrix U and, oh sorry, not m by n, m by m orthogonal matrix U and an n by n orthogonal matrix V such that A is equal to U times sigma times V transpose. That's the theorem. That's called the singular this decomposition of a matrix A into this product U times sigma times V transpose, that's called a singular value decomposition of A. Okay, so in the rest of this video, I'm going to prove that this theorem is true. And basically, the theorem comes from constructing the U and the sigma. Well, we've already constructed the sigma here. So we really need to just construct the U and the V and show that A is in fact equal to U sigma times V transpose. So I have to tell you what U is, and I have to tell you what V is. Well, recall that above, what we found was, what we picked, what we chose, is an orthonormal basis for Rn consisting of eigenvectors of A transpose A, and we called it the set V1 through Vn. So if you take those VIs and put them as columns of the matrix, that's like the Q in the Q lambda Q inverse decomposition, we're going to call that V. So we define, so here's the proof of the theorem, we define V to be the matrix whose columns are V1 through Vn. Well, we know that the VIs are unit length and they're orthogonal, so the VIs are orthonormal, and this is an n by n matrix, right? These are n vectors in Rn, so this is a square matrix with orthonormal columns, and therefore it's an orthogonal matrix. So by how we define the VIs, this is an n by n orthogonal matrix. Now we have to define the U, the vector U. So what we do is this. For I equals 1 through R, okay, R is the rank, so you don't go all the way to n, you only go out to the rank. Define UI, the vector UI, to be 1 over sigma I A times VI. So first of all, you only can go out to the rank because, as I said, if you go out past that from R plus 1 to n, those sigma i's are all zeros. So this thing is, not defined, right? Otherwise you'd have 1 over 0. So this expression, ui, only makes sense for I equals 1 to r. Okay. And this is, so A times VI, right? A is an n by n matrix. So A times VI is an element of Rm, and I'm just dividing by sigma I. So this is a vector in Rm. And remember what we said about the singular values. These sigma i's are the singular values. We showed above that they're the lengths of the A times VI's. And so what we're really doing is we're taking A times VI and just normalizing it by dividing by the length. So this is a unit vector. These UI's are unit vectors in Rm. I have R of them. Let's check that they're orthogonal to each other. So if I take the dot product of ui with uj, that's ui transpose uj, and this is going to be, by definition of the ui's, 1 over sigma I times sigma j, A times vi transpose A times vj, right? Because I have these constants, sigma I and sigma j, I can pull them out, and then I have the dot product is just this matrix product. And this is going to be 1 over sigma I times sigma j, vi transpose A vj. Okay, again, we're using this property of the transpose of a product, A times B. The transpose is B transpose A transpose. We use this a lot in this discussion of orthogonality and dot products. And now I have A transpose A Vj here. Well, Vj was an eigenvector of A transpose A with eigenvalue lambda j. So this is going to be 1 over sigma I sigma j Vi transpose lambda j Vj. And of course I can move the constant, this lambda j is a scalar, I can pull it out, and I'm going to get lambda j over sigma I sigma j Vi transpose Vj. Now what is this going to equal? Well, if I is not equal to j, by the way we defined the VIs, we defined these VIs to be orthogonal to each other. So if I is not equal to j, what's Vi transpose times Vj? It's 0, because these vectors are orthogonal to each other. Now what if I is equal to j? If I is equal to j, what we get is, so if I is equal to j, then we get lambda, okay, they're all the same, right? So lambda I over sigma I times sigma I, that's sigma I squared. And that's V, and then I get Vi transpose Vi. Well, this lambda I divided by sigma I squared, we define sigma I to be the square root of lambda I. So that quantity is the scalar 1. And Vi transpose Vi is also 1, because we defined Vi to be unit length. And 1 times 1 is 1, so you get 1. So this shows that these UIs are orthonormal. They're well, we actually knew that the UIs, sorry, we already knew that the UIs were unit length, so I guess we already knew that UI transpose UI was going to be 1. Okay, the main thing is now we also know that they are orthogonal, because we see that if I is not equal to j, then UI transpose uj is equal to 0. Okay, so we have that the UIs are orthonormal vectors in Rm, but I have R of them. And what we can do is we can extend the set U1 through UR to an orthonormal basis. U1 through UM of Rm. Okay, why can we do this? Because once you have, so there's a general procedure, there's a general theorem that says that if you have a subset of Rm, so if you have fewer than m vectors, you can always extend that set to a basis for Rm as long as this set that you have is linearly independent. You can always kind of throw in more vectors to form a basis. So that will give you a basis for Rm, and then you can use Graham-Schmidt to make that basis orthonormal. So that's how this works. And now you define the matrix U to be the matrix U1 through UM. And notice that this is an m by m orthogonal matrix. So now we have our U, we have our sigma, and we have our V transpose. Well, we have our V, and so that gives you the V transpose. Now we need to check that when you multiply them all, you actually get A. So if you take A times V, what are you going to get? Well, that's going to be A times the matrix whose columns are V1 through Vn. And that's going to be, so what are we going to get? For I equals 1 through R, you're going to get sigma 1 V1 to sigma R VR. Okay, why is this true? Let's see here. Why is this true? Let me take a look at the textbook. Sorry, let's see. There's also an issue. How do I know? Is this supposed to say A transpose A? I think this is supposed to say A transpose A. No. Sorry. This is supposed to say U1 through UR. There we go. Sigma 1 U1 to sigma R UR. Okay, why is this true? Because by the way we define UIs, right? We define the UIs to be like this. So if you multiply both sides by sigma I, you get that sigma I UI is equal to A times VI. Okay. So that explains, and that was only from I equals 1 to R, exactly. So that's how we get this. And what about the rest? So why is A times... Okay, so this was what I was saying before. So, how do I phrase this? The V1 through VR are the vectors such that A times VI is not 0. And the VR plus 1 to Vn, these are vectors in the null space of A. Okay. And so that's why you get 0 for the rest. And then when you take U times sigma, you get this matrix, which is U1 to UM. And then when you multiply by sigma, capital sigma, it's this matrix where you have sigma 1 to sigma R and then zeros everywhere else. And what that's going to give you is sigma 1 U1 all the way to sigma R UR, and then the other columns will be 0. And so therefore we see that A times V is U times sigma. So A times V is U times sigma. And now we multiply both sides by V transpose. A times V transpose is U times sigma times V transpose. And V times V transpose, since V is orthogonal, V times V transpose is the identity. And so you just get A equals U sigma V transpose. And that's the proof of the singular value decomposition. Okay. Okay, so that was the singular value decomposition, and in the next video we'll do some examples. Thanks.